So we've developed a solid understanding of the equilibrium constant, how to write equilibrium expressions, and use ice tables to calculate concentrations of a reaction to equilibrium. But it's really important to see the connection between where the idea and concept of an equilibrium constant and expression comes from based on our knowledge of kinetics. So let's consider the reaction, something simple like A plus 2B is in equilibrium with AB2. We know that if this is a reversible reaction, indicated by the arrow here, going both ways, we can calculate the rate for both reactions. We can calculate a K forward, and we could also calculate a K reverse. Let's use a different color here to indicate K forward. And now we also know that at equilibrium, that means the rate of the forward reaction equals the rate of the reverse reaction. So rate F equals rate reverse. Okay. So how can we write rate laws for both of these reactions? Well, remember a rate law for the forward reaction would be something like rate forward equals the rate constant, which is Kf, times the concentration of A times the concentration of B squared. And we would know the rate law for the reverse reaction would be Kr times the concentration of A, B, 2. Because in this case, the reaction would be going to the left, and so AB2 would be our reactant. Well, since we know that at equilibrium these rates are equal, we can set them equal to each other. So we could say Kf times A times the concentration of B squared equals K sub R times the concentration of AB squared. So now if we set up a ratio of K forward divided by K reverse, so divide by Kr on both sides, we'll be left with Kf over Kr is equal to AB sub 2 divided by, and I'm just going to move all of these over, divided by AB squared on both sides. So I have A times B squared. So instead of writing this as Kf over K sub R, all we write that as is Keq, the equilibrium constant. So that's the derivation of where the equilibrium constant comes from. The concentration of the products, which we see are AB sub 2, divided by the concentration of the reactants, AB squared. But what is important to notice from this, since the equilibrium constant Keq was derived from the rate law, okay, this comes from the rate law, it is only affected by things that affect the rate law. And we learned, according to the Arrhenius equation, the only thing that will affect the rate constant for a particular reaction is temperature. So if you want to change Keq, you have to change temperature. Otherwise, changing reactants, concentrations, changing pressure, that will not change Keq. It will shift the reaction one way or another. But the only thing you can do to change the value, the numerical value of Keq, is to change the temperature.